5.3 Definite Integrals. This is video 1. We are going to go ahead and talking about we're looking for an easier way, knowing that we want to take large numbers of subintervals to find the area under a curve. There's got to be something a little bit better than what we've been doing. But before we get to that, I need to start talking about, well, everything we've been doing has been a graph above the x-axis. So now the question becomes, what if we're below? And say I have a function that may look like this. So if I go ahead and I'm doing my subintervals and I have my little rectangles, and we see we're doing the same thing over and over. It's the same process, but the key thing to remember is that my y values or my heights are actually now dealing with a negative y. So that I have technically a negative area for under the graph, for under the x-axis. So between the x-axis and the function that is below the x-axis. So then we want to talk about, well, what if we have a function that is actually maybe a combination of both, something that looks like this. And so I'm really talking about the different areas that I would have the positive that are above the x-axis, and then I would have negative area that is the part below the x-axis. So I'm still always finding area between the x-axis and the function, but whether or not the function is above or below the x-axis. So that's the case, I'm going to have to subtract the area above minus below. So I'm going to use, and this is what we call net area, the total net area. So if that's the case, the definition of net area is the region R bounded by the graph of a continuous function and the x-axis between values of a to b, and the net area is the sum of the areas of the parts that lie above minus the area that lie below. So we do have that we want to talk about today, and I'm going to do a couple examples. And then I want to go ahead right now, right into the definition of a definite integral. It's a function on a closed interval from a to b that is integrable. It means we can take the integration of it. And it says here we're going to use this definition of the limit. Well, wait a minute. What does that mean? We know the Riemann sum from the previous section, and where we want to start from our lower limit to our upper limit. And we're going to basically be doing the heights times the widths of the rectangles, and we're going to sum up these areas. But now what we're talking about is we want to know when the limit of this, where the delta is approaching 0, meaning we want this, the delta x part, to be as infinitesimally small as possible so that we can have an infinitesimally amount of, or infinite amount of rectangles under the curve to get the best approximation, or see if we can find it exactly as we could. So this is where we're saying the limit as the delta is approaching 0, as our widths get as small as possible. So then we're saying this whole definition, that what I have written out in the red, is the integration of from a to b, our lower limit to our upper limit, of the function, which are the heights times the widths. So it's area. It's everything we've been doing now, but using the correct integration notation. So we're going to go ahead and do a few examples. So I'm going to start with number 12. Number 12, we're given this function f of x is equal to -4 minus x cubed on the interval from 3 to 7. And the book wants us to graph it, and I'm going to do a very quick sketch. and it technically graphs like this below the x-axis. And they want us to know then, after we graph it, if we can go ahead using subintervals of 4. So basically, we're going to have a width of 1 because our delta x would be, oops, sorry, 7 minus 3 divided by 4, or 1. And they want us to do left, right, and midpoint. And at this point, I did just use my calculator program, and I got these numbers. Left, right, and midpoint. Oops, sorry, that's RAM. Okay, so obviously we see left was under, right was over, and our best one right here is the midpoint approximation. And since it is below the x-axis, all the values are negative. If we want to go ahead and try another one real quick, 17. I have sine of 2x on the interval from 0 to 3 pi over 4. And I highly recommend trying to sketch this one without a calculator. Just remember all of your trig and what we had from there. So I had, if I have pi over 2, a pi over 4, 3 pi over 4. Remember that our signs go from 1 to -1. If I draw our function, it should look like this. And from here, we see that we have areas above and we have areas below. And I want to go ahead and I just use the calculator again for left, right, and midpoint. For left, we're approximately 0.735, approximately 0.14 for right, and mid was 0.530, approximately. This one, though, on this problem, I'm going to do C that actually is asking me what intervals are positive and what intervals are negative. We see from 0 to pi over 2, oops, we are positive values, and from pi over 2 to 3 pi over 4, were negative values. Notice I did not include the 0 in my subinterval in the first one because it's neither positive nor negative. So we're going to go ahead and do some more. That I want to go ahead. 23 says, given this definition where we want the limit of delta approaching 0 of the summation from k equals 1 to n of x sub k and it's squared plus 1 delta k sub x on the interval from 0 to 2. They want us to use this definition and put it into integral notation. So what we want to do is we know we want to have the integral, and our bounds are going to be from here, a to b, lower to upper. And then we can see that we need f of x. We know this is our f of x, but in its notation here in terms of x, we're just going to use x squared plus 1. And this quantity is going to be multiplying delta x, but in the integration notation, we use dx. So we have here our function. We're trying to find the area, and we have it in the Riemann sum limit notation, and then we have it in our integral notation. So then you want to go ahead and do number 26. The book is giving us the integral notation of this function, but they don't want us to calculate in this method yet. What they want us to do is go ahead and use geometry. They want us to graph it, and then they want us to use geometry to find area. So from here, if I was to graph this function, My graph is a little off scale. But I have this, and you can see I'm above and below the x-axis. So I want to find areas that are this triangle, easy to find, and this triangle, easy to find. But remembering that the above is positive and below is negative. So if I wanted to do that, I have the area, and I'm going to use formulas for a triangle. 1/2 the base, and I'm going to be doing the one that's above. And I notice I have 1, 2, so I'm going from 1, 2, 3, 4. And a height of, when I plug in 2 into the equation, I see that this is at the point 2, 8. So a height of 8. And then I'm going to be subtracting the area below, because really it is a negative height of 4. So I could say plus, but I'm going to leave it as negative because I know it's below my x-axis. So I'm going to do 1/2 times the height times the base. My net area for this should be 16 minus 4, or 12. So we do have a number of problems for homework that are in this situation. I'm going to do one more for us because we're trying to do this with geometry. I have this function, and it turns out it's a piecewise function. This function does graph continuously, though it does have a corner. So here at 2, we have a problem. But if I break this up using geometry, then I shouldn't have any problem. So from here, I'm going to use a rectangle for this one. And then I'm going to use the area formula for a trapezoid on this one. And then I can add them together. They're both above the x-axis, so they're positive. So from here, I have the area of the rectangle being 5 times 2 plus, and then I'm going to use the area of a trapezoid, which is 1/2 of the bases added, which would be 5. And when I plug 4 back into this bottom half of this piecewise function, the height on this one is 11. So it should be 5 plus 11 and times the height, which is 2. This is a trapezoid on its side. This is my height here for h. And then I'm going to go ahead and calculate. I get 10 plus 16, and it equals 26 for the area.